Good day, dear students. Today, in the topic, we will discuss about the matrices for a general linear transformations. As we already discussed that behind the linear transformation, there is a standard matrix, but we can see that if we have some basis for a domain set of a mapping T linear transformation from V to W, then we can also find a standard matrix corresponding to the basis set B for a vector space V. We can also get for Tx where B prime is the basis for a set W, and this technique is also quite useful to get the standard matrix of a linear transformation. For this, if we have any finite dimensional uh, vector spaces V and W, and if T is a linear transformation, then there are some steps to find Tx. For example, compute the coordinate vectors Vx from the basis set B, and then we multiply these bx on the left by a to produce tx. Tx, it is just like a times x. We know that tx will give us a metric a, and after that we multiply a with x, and then reconstruct tx from its coordinate vector tx under the B star. And here we will see its examples and certain criteria. It's a geometrical representation. We know that if T is a any linear transformation, then in a finite dimensional vector space, then we can find a matrix A of m cross n, and it will be just equivalent form of that one, that ax beta or b is equal to tx beta or b prime in this form, and where beta are the basis for a vector space V, and b prime is actually the basis for a range set W. And the idea is quite simple. For example, you know that if u1, u2, these are the bases, then we just apply the t of u, and it will be equal to t of u1 is equal to tu1, and just take these elements over here in the form of that one. And with if we multiply a metric A with these kind of say u1, u2 on the left side, u1, u2 up to un, all of that one, and then with the multiplication we will get these vectors. Then these are called the images, or images of t, like tu1, tu2 up to that one. And if we combine all of that one and write as a single metric A, then this will give us basically the matrix for t relative to the bases b and b prime. This is from b to b prime. In this way we can get the elements, and so this is also the interesting idea to get the element of that one. And for this there is a simple example, but remember that in that all this case we must have a finite dimensional domain, uh, finite dimensional vector spaces in the basis in the domain set as well as in the range set, where T is a linear transformation from Rn to Rm. For instance, if we take a linear transformation T from P1 to P2, P1 a polynomial of degree 1 to polynomial of degree 2, its transformation as a Tpx equal to x time px, means just x multiply with any polynomial of degree 1, then it will becomes definitely to the polynomial of degree 2. Then find, for example, find the matrix for T with respect to the standard basis beta of u1, u2, and b prime beta or b prime of v1, v2, v3. Remember that every finite dimensional vector space have a basis, but one of that is the standard basis. For instance, for P1, the standard bases are 1 and x. For P2, the standard bases are 1, x and x square. Similarly, for R2, the standard bases are 1, 0 and 0, 1, like these two elements for R2. Similarly, for matrices and all, they have a standard basis as well as. So now, look, the idea will be quite same. If we put t at the first element of a basis set like u1, it will give us x times 1, because 1 is the element over here, and then it will becomes x. And when we put t on u2, second element of a basis, it will gives us x square. So basically, it means from the first element what we get, this element, and the image of t is actually a polynomial of degree 2, but as we have noticed that here it's only give us the x, so just pick up the coordinates of that one. So one can write as a 0 plus 1x plus 1x square, so 0x square. So it means 0 1 0. These are the elements, like these are the coefficients of a 0, the constant, then x, then coefficient of x square. And similarly, if you put the second element of a basis x under the t, then it will gives us x square. So it means the coordinate vectors are 0 0 1, means 0 0 constant plus 0 times x and 1 times x square. So these are the elements. Just write like we combine this one as a TU1 and TU2, then we will get a matrix of T with respect to beta and B, or B and B prime is this one. So this is the simple idea to get the standard matrix depending upon the basis set. Now, there are also some other procedures like three-step procedure for which we can employ to get the value. For example, if we have a T is a mapping from P1 to the P2, P2 which is a linear transformation, and take the elements like in this way. Then we can sometimes multiply the elements and get their entries. For instance, if x is a polynomial, so just take its coefficient a and b relative to the standard basis 1 and x, and then multiply with this matrix, the metric t, t of that one with this element, this coefficient a and b. Then if we multiply this, we will get tx under on the b star, like this will be the element on the other side of that one. And then we can reconstructing tx, where x is equal to a plus bx from this transformation. Like if we just put t on a plus bx, then the image will be 0 plus ax plus bx squared. This means it will be ax plus bx squared, like just the same element as a x multiply with the a plus bx. So in the next example, you can see that if T is a linear transformation, which is T is a map from R2 to R3, which is in that form. And we know that behind a linear transformation, there is a standard matrix. So we can take the elements in that way, like just this is the element x1, x2 is from to R square. And so we can write here x1, x2, and over here we can write the coefficient matrices of that one, which is like which will be equal to, for example, it will take the elements 0 plus x2, it means 0x, and similarly minus 5, 13, minus 7, and 16. So we can get a standard metric of t. So, and like if the basis b, B is the basis for R square and B prime is the basis for R cube. For example, if for the particular case U1 and U2, these are the basis for R2 and these are the basis for R3, then from this we can get the formula for T. For example, if we put the value of a 3 1 in T, like T of 3 1, if we apply the elements over here, then we will simply get the element in R3, which is 1, minus 2, and minus 5. And if we put the second element of a basis, U2, like 5, 2 in T, then it will gives us the image, which is 2, minus 1, and minus 3. So when we get these two elements over there, then we have noticed that we can express these vectors as a linear combination of v1, v2, and v3. Like this, the elements 1, -2, and -5. So, and the other element is TU2, which is the element as a 3v1 plus v2 minus 3. So, we just express these as a linear combinations of v1, v2, and v3, the element of that one, TU. For example, if you write as a this vector as a linear combinations of v1, v2, and v3, then this expression will give us in that form. Here, when we will make a linear combination of that form, so it means just can write 1, -2, 5 as a column vector and express with k1 v1 plus k2 v2 plus k3 v3. And by after solving that linear system, we can get the value of k1, k2, k3. If you solve the k1, k2, k3, so definitely k1 will be 1, k2 is k2 is 0, and k3 is -2. Similarly, for the other values, if you take 2, 1 minus 3 on one side as a vector is equal to say k1 v1 plus k2 v2 plus k3 v3, and after solving and comparing the coefficient, it will give you a linear system. And by solving that one, so simply we will get the elements of the coefficients k1 equal to 3, k2 is 1, and k2 is -1. So it means these are the entries of that one. So if you again write them like these images as a 3D, for example, we know the value of a u1, u2, u3. So just put the values over here, and after the computation, like we will get these values. For example, it's a 1 0 -1, and the second one is the 0 1 2. So multiply with the 3 of that one is, and after putting this value and computation, we will get the element 1 0 -2. Similarly, the value of TU is this one. So put the value of v1, v2, v3 here, and after the computation, we will get this vector. Now, as we know that if we combine TU1 and TU2, so it will give us a basis for a T beta, TB. But since these are the images of that one, so this is called the basis, the matrix of a TB star from B. So if you combine the first TU B prime and TU2 B prime, like both of that one, so it will be the value of a matrices from matrices of T beta, T B prime from B. So this is the simple way regarding that one. And similarly, there are some other examples one can generate, for example, in R2 to R3 and from the polynomial and from the matrices. So it means for all finite cases, we can do the same procedure. Now, it means that if T is a matrices behind, if the T matrix is available like this one, which is the standard matrix of this linear transformation, then this basically T T under B prime is a standard matrices of its images element from based on the B prime from B. Like these are the bases available for that. Now, this is the idea, as we know that TB, we can just combine TU1, TU2, and up to TUN from the B set B of that. And behind the linear transformation, there is a standard metric, and we can get the standard metric, which is based on the basis set B. Normally, or in some cases, we can take B as a standard basis of the domain set. Also, there are many examples for identity operator. We know that there is a linear transformation. In that case, the B and B prime will be the same. So this is the matrices of a identity operator. We can just simply write IB, which is the images, which we just take the coefficients, and this is the standard metric for a basis set beta, where beta is the standard metric. Because I is a derivative operator, it always be a standard metric. Here in this example, you can see that if T is a linear operator Y, because it's a transformation from P2 to the P2. The same domain set and range set are the both are the same three-dimensional vector spaces, which is P2. P2 is a polynomial of degree 2, which dimension is 3. Now, if we apply the T on Px, so element will be equal to the P time 3x minus 5. So this is the transformation. So that it means that if we put any polynomial of degree 2, so instead of x, x will be replaced with 3x minus 5 on that is. So this is the mapping. Now, the question is the find standard matrix uh, relative to the basis B set, which is a standard metric of a polynomial of degree 2, 1x x squared. This is a standard metric, standard basis of a polynomial of degree 2. Now, also use the indirect procedure to compute T of the image of T of 1 plus 2x plus 3x square, and also check the result by computing T1 plus 2x plus 3x square. Here the procedure is again the simple, like if we put the standard, like we have a basis set over here. So if we put the values, for example, in T of 1, 1 mean C1 is 1, but the rest of C2 and C3s are 0, then it will becomes T1. Then if you put C1 as a 1, and then it will be image will be equal to only 1. And when we put the second element x from the basis set, then Tx will be equal to, in that case, C1 is 0, C1, C0 is 0, C1 is 1, and C2 is 0. So it means only the x putting over here. So the image will be 3x minus 5. And moreover, for the last element, for T of x square, C1, C0 is 0, C1 is 0, and C2 is 1. And the image will be only the 3x minus 5 whole square. So if we open this square formula, we will get 9x square minus 30x plus 25. Now, by these values, we can write this and in the matrices form of the first write into the vector. We know that the each element of R2, like these are from the basis from the range set. So the range is also the P2, and the coefficient we can write as a 1, 0, 0, because 1 is only over here. There is no coefficient of x and no coefficient of x square. So it will become 1, 0, 0. Here we have minus 5, the coefficient of a constant, then like the coefficient of a 1, and the coefficient of x is 3, the coefficient of x square is 0. So just take the coordinates from that and we will get the coordinate vector. Similarly, the coordinate vector of a tx square is like 25 minus 30 and 9. And now again, if we combine this one, we will get the standard matrix relative to the basis set B 1x x square. So this will be the value for that one. And now, as in the next part, use the indirect procedure to compute t at 1 plus 2x plus 3x square. So it means just take the value over there one and relative to the basis b1 x square. Now, as we notice that the coefficients are 1, 2, 3. So it means that with this we can just put 1, 2, and 3, the coefficients over there, and then we will get a particular value from that. And the other cases, in the other case, for example, if we have a TB, then from this we can get the coefficient of this one and just multiply. We will get the coefficients of a constant x and x square. So this will be equal to the TP of B. So again, just write this in a polynomial form, the coefficients of constant or coefficient of 1, then coefficient of x, and then coefficient of x square. So this is the indirect method to compute this value. And by the direct method, just simply put the t instead of C1 is 1, C2 is x, C3 equal to x, C naught is 1, C2 is C1 is 2, and C2 is 3. Like we just put the coefficients value over here. So C not C1, C2 values, just like at this we have 1, 2, and 3. Then after the computation, we just simply get uh, after simplification, we will get this as a image of a 1 plus 2x plus 3x square. So this is the result, or this is the direct computation method. So then in the next result about the matrices composition and also inverse of that one. So this is also the interesting idea. For example, we have a if we have two linear transformation T1 from U to V and T2 from V to W, where U, V, and W's are the finite dimensional uh, vector spaces. And if B, B prime, and beta, B prime, and uh, beta B prime, and B double prime are the basis for a U, V, and W, then one can see that T2 or T1 of B and B prime B will be equal to in that form, like B prime, B double prime, and then B double prime B. It will be split in this way. And there is a good thing is that of that one is that they are not like as a composition, but only the matrix multiplication. And moreover, the next result will be tell us about its invertibility or inverse of that one. Like if T is a linear operator, if this is linear operator, then it means behind their standard metric A is n cross n, because we are talking about finite dimensional vector spaces V. And T is a linear operator, and if B is the basis for a V, then the following are equivalent. Like T is 1, 1. You know that if T is 1, 1, then it means the metric A is invertible. If metric A is invertible, the same metric, the T of beta under the entries of beta is also invertible. And moreover, if we take T inverse of the beta, that will be equal to just like a T beta whole inverse. So this is also the equivalence form of that is. And moreover, if we have a composition idea T3, T2, T1, then it's again the same splitions of its basis of that. This is also the same, and it's just like the extension of this one. And there is an example regarding that one, which says that if T1 is a mapping from P1 to P2, which is a linear transformation defined by T1 of Px equal to xpx, and T2 is again an linear operator. Just P of x will be changed as a 3x minus 5 in the polynomial in place of x. Then we can get composition like T1 will be gives us a simple x multiply with Px. Then it will becomes the entry of a polynomial of degree 2. And if we take that one, first apply the P1, sorry, apply the T, and then secondly, when the image will come, Px, then we apply the T2 of that one. So T2 means just it will multiply, it will change Px as a P of 3 minus 5. So this will be the outcome of that one. So it means in general, if Px is any polynomial of degree 1, like Px equal to C naught plus C1x, then we can just put the value x as a 3x minus 5 over here, and then it means it will gives us the value like in this way. For example, like we just simply get its form T2 or T1 is equal to on C naught C1x equal to this one after just simple simplification. And now, if we take the standard basis for a P1, which is 1x, and the standard basis of a of P2, which is 1x x square, then we can take T1 as a, we know the standard basis of a T1 is under from B star to B is it's just take the multiplication entry x with its element. So the coefficient of that will be the 0, 1, 0. and 0, 0, 1. This is the same as an example 1 we have seen before. And similarly for the T2, which is as an example number 5, we see that if we have the matrices in that form, if the T2 is a polynomial, T2 uh, is a linear transformation from P2 to P2, then it means the matrices form is this one. Now, one can check that if we take T2 or T1 and take its basis B prime from the B, then it is just multiplication of a this T2 matrix multiply with T1, and we can see that this result validity will always be hold. For example, if we multiply, we will get this one, and this entry is also the same as if we take composition of this one. For example, one can take notice from there that the entries are a -5 and minus 5, 3, and the x square coefficient is 0, so here 0 comes. And secondly, if you open the second entry, then still we will get 25 minus 30 as a coefficient of x, and then the coefficient of x square will be the 9. So here we will get the same thing, and one can see the validity of this, which will be always hold in that case. So one can make it separately, or one can be combine it. In both cases, one can see that this result will be always true, and we can write the thing in this way. That is all about these matrices of a general linear transformation. So here there are some problem arising. For example, if the matrix of a linear transformation T from V to W uh, relative to some basis of V, and W is actually equal to the 2, 0, 4, 3, then there is a non-zero vector x in V such that Tx is equal to the 2x. So remember that here there if there we have a standard metric of that one, so for which element in a domain set if we put over there, then that vector will be a non-zero, and if we multiply with that metric we will get the answer like same as a 2x. So in that case, if we take for example this is x is in the vector over in a like there are element in R square, and 2 is also the element over there. So if we multiply the like x will be the same, so it will becomes like 2 times x. Then after the multiplication, like if you have a 2 and 4 multiply with any non-zero x1 and x2, so we can see that the image will be equal to the just 2 times of that x. So which it will becomes like 2 times x1 plus 4 times x2. So it means that this element will be not available in that case, unless for that this equation is not hold, because the first entry multiply with the 2, second entry will be multiply with the 4 in that case. And if again if T is a transformation from V to W, uh, which is related to the basis for V, and W is this one. Like if we have this one is available for that, and then there is a non-zero vector x in V such that T of x is equal to the 4 times x. Now notice that the first element will be multiplied with the 2 and second will be the 4. It means like if we take x1 and x2 of that and see that it will becomes 4 time of that one. So the idea will be like if we take the common from that, the first element is give us a the entry which is multiplied with the 2 and second will be the 4. Then it means that there is no element which have the same factor common from that. So it means this statement is again not fulfill the criteria that X will be a non-zero vector, which satisfies Tx equal to the 4x. And if the metric of a linear transformation T from V to W, which is relative to the certain basis for V and W is equal to 1, 4, 2, and 3, then T is 1, 1. We know that behind the linear transformation there is a standard metric, and if that metric is invertible, then it means if that metric is invertible, then it means T is also invertible. I like T inverse exist or T is 1, 1. And we know that how to get the matrix is invertible or matrix has inverse exist. Just take its determinant. If determinant is non-zero, then it means it's invertible. The determinant is 1 multiplied by 3 minus 4 multiplied by 6. So it means it will becomes like 4 multiplied by 2, which is 8, like 3 minus 8, which is minus 5, like 9 non-zero. If this matrix determinant is non-zero, determinant is like minus 5, which is non-zero, it means A inverse exists. If A inverse exists, it means this T inverse also exists and means T is invertible as well as T is 1 to 1. Because if T is 1, 1, then this is invertible. So this statement is true. And if S is a linear operator, V is also linear operator from V to V, and B is the basis for a V, then the matrix of S O T relative to the B, and B is TS, T, B, and S like this. So you remember that, for example, if we go over here and we can see that if we take its standard matrix, so then it will becomes T3, T2, or T1, like in that form of that will be its form. For instance, over here, like the matrix of ST will be equal to S first and T second. We know that the matrix are non-commuting, so S will be also in the S must be on the first side and T will be on the second, like because they are non commutative. Like the matrix A times B is not equal to B times A always. So that's why this statement is not true. And if T is a mapping from V to V is invertible linear operator and B is the basis for V, then the matrix for T inverse relative to B is T B whole inverse. This is true, like we have already seen that if this is the this, if T is invertible, then the T inverse is also invertible, and the matrices of T B inverse is equal to uh, T B a whole inverse like of that. So this statement is correct because we have already see this thing over here. There is some example regarding that one. Like if T is invertible, T is 1 1 mean T is invertible. Then it means this is invertible and it's a T inverse matrix of the B is same as TB whole inverse. Just one can get the metric A and find its inverse. So this is its equivalent form. So these are the problems regarding this. And now let's come towards some problems of that one. So if let V and W be the finite dimensional vector spaces where dimension of a W is less than dimension of a V, then show that there is no one linear transformation T from V to W. It means look like if you can see the example, T is like a mapping from R3 to R2 or R3 to R1, where the dimension of R3 is 3 and dimension of W is like our dimension of R2 is 2. So one can see that in case of a basis set of that, because they are finite dimensional, it means they must have a basis. So one can see that there is no one correspondence exist for that. And if there is a 1 1 corresponding exists, then it will make a contradiction. So this is a simple general result regarding that. And in the next problem, if T is a mapping from vector space V to V, like it's a linear transformation because T of a V is same as 1/3 of V, then find a transformation T2 from V to V such that, like, if you multiply T1 with T2, then its image is identity and T2 or T1 is also identity. It means T2 is the inverse of a this linear transformation, and we know that this linear transformation is invertible. Why? Because if you put 0, the answer will be equal to the T1 of 0 is 0, and there is no any other element for which the image of T0 is 0. It means this map only maps 0 to 0 only. So this is invertible, and one can find its inverse, which is very simple. And I hope you can get some vector for which, if you multiply T1 with T2 on V, the answer will be again V, and T2, T1 of V is also equal to the V because I of V is V, where I is identity identity operator. Now, suppose that if T is a linear operator from R3 to R3 defined as this way, X plus Y, X minus Y, and Z minus X. Then find a standard metric T with respect to the bases. Here, basis at B is available with V1, V2, V3, and this is very simple. Like you just put the elements V1 first of all over here, then V2, and then V3. And if you combine all the images over there, then one can simply get a T of a T matrix T from this basis B. So this is a simple question regarding that one. And the problem number 38 deals with the if T is a linear transformation from M2 to M2, which is in that form, then find its eigenvalues and eigenspace of T. Eigenspace mean eigenvectors of corresponding eigenvectors. As it's a 2 cross 2 matrix, so one can simply get the eigenvalues and eigenvector in general in terms of a, B, and C of that. So this is just will give you simple sum equation, and when you will put the values over there, then still we can find the eigenvalues and then corresponding eigenvectors. So these are about the problems. And now, if you have any question, you can ask your question.
No questions.
Okay. Okay, fine. If there is no question, then we will stop the session over here. Best wishes and goodbye now.
Thank you.
Okay, goodbye.